profile. Professor Berg studied economy here at the University of Bonn a few years ago. He left Bonn after his graduation to the United States, Munich and Hanover, where he obtained his professorship, and he performed it. He was back in Bonn as a dean of the Department of Economics for a couple of times. His main research comprised dynamic systems analysis, what he will talk tonight to us, environmental and resource economics, and risk management. As was said in the invitation, this talk is the kickoff for a small group that we're trying to set up. And when I say we, I mean Franz Gassweiler and Saravana, who are sitting that way, on complex systems analysis, or business system development. I will try to link these two ideas, complex systems and development. And nobody better for us to give us this talk that Professor Berg made. Professor Berg, it will last about 45 minutes, he told me, and then we'll have about 30 minutes for questions and answers.
Well, thank you, Daniel, for the introduction. When this report you mentioned, the Club of Rome on the limits to growth, was published, I was about the age than you are today. So I have quite some time of experience with modeling. Actually, I came across system dynamics and systems modeling at the time when this report to the Club of Rome was published. These were the early days of computing. You had to use mainframes and punch cards and all such stuff. And I couldn't even play with J.W. Forrester and Dennis Meadows models on my own, because we had a nice mainframe computer at the University of Bonn at that time, but unfortunately it was an IBM. And it didn't have a Dynamo compiler, so there was no way to run the model actually. However, I had a chance to go deeper into this sort of modeling and approach to modeling also when I got the opportunity in 1980-81 to spend a little bit more than a year, 13-14 months at Michigan State University. And that is, in these days, Michigan State University, the econ department especially, was quite famous for doing such types of modeling. Specifically in the area of development economics. One of the big guys those times was Glenn Johnson. I was there as a postdoc fellow, and I got a lot of this experience on the methodological part. And of course I took courses in quantitative modeling, because the systems approach always has two parts. One is the methodological approach of how you go about problem solving, and the other one is the instrumental part, if it really comes to quantitative modeling. I have to admit I've been a modeler all the time, more on the instrumental side than the methodological side, but with some decades of experience, one has to develop his own experiences of how to go about modeling, how to start, when to decide that one is probably in a dead end road, change direction, go somewhere else. So what I want to do, next 45 minutes or so, I'm going to share with you some of my experiences I have made. And what I also want to do, I'll try to attract you to do modeling on your own. So I'll present some ideas on how we go about modeling, what are systems, and how do we go about systems modeling. And at the end, I present you with some instruments, nice small models, which however show quite complex behavior. And well, while I'm giving my presentation here, feel free to interrupt me anytime. If you have a question, ask them. I'm not necessarily aiming at giving a 45 or 50 minutes talk and then having a discussion afterwards. You can always interrupt me and we can go into discussion right away. Let's start looking at what we understand with the system. In essence, I view a system as a box, if you want, black box at the moment, where we have a transformation of inputs into outputs. If you look at the inputs, they can be of two categories. Either they are instrumental variables, which are under control if it comes to managing such systems, or they are non-controllable environmental variables, which also influence the system. The outputs are state variables and outputs. The distinction between state variables and outputs is pretty important because state variables are the important ones, which actually, when it comes to dynamic systems, contain the whole history of the system. Dynamic systems always have a history, and the history always gets completely captured in the state variables. So if you are able to completely identify the vector of state variables, you have the necessary information to completely represent the implications of the whole history of the system. We'll come to that later on. And then we have a system structure, and the system structure essentially forms the functional relationships that convert inputs into outputs. When we talk about systems, we always have in mind that we have these three categories of variables and the system structure, which is which forms in the quantitative modeling forms the functional relationship, if you want. Now, if we use such an image for problem solving, we have to somehow represent the system in terms of a model. Where modeling is basically nothing special, because problem solving in general, if you do solve problems, you generally base that on subjective and crude images of the world, which are models, which are implicit models that everybody has in the back of his mind. What we do if we develop explicit models is that we make this process explicit. The development of models for problem solving as well as thinking in models is quite common procedure. However, a procedure that mostly takes place unconsciously in everybody's mind. We are, if it comes to problem solving, normally reductionists. We look at the problem, which is often complex, and then we take away all aspects, remove all aspects which we think are not necessary, to focus, to concentrate on the main aspects. And then we have some ideas about cause and effect, which may come from our personal experience and our background by training. And then we use these ideas to come up with a conclusion. Formal modeling is nothing different. It just makes this process explicit. However, we normally start with our implicit model. The term original, which I used here, is, if you want, an artificial term. Because we are never sure that our view of the world is really the true original. Okay. Before Copernicus, everybody thought this planet would be a plate. And all cause and effect relationships people had from experience those times are quite different from what we have here. we view the world with our sense, with our ability to view the world. I've heard that there are birds around which have a 4-color scheme viewing the world instead of the 3-color scheme we have. To view the world in the 4-color scheme, it must look quite different than in the 3-color scheme. And some people don't even have a 3-color scheme. There's a color missing. If there's a color missing, the world looks quite different. You never know whether your view of the world is the true original. So the starting point for any modeling procedure is your personal view of the world or of the problem at hand, and this personal view is always biased by your own personal experience. This is important to note because that's the reason why we never find the model to represent a particular problem. We have as many models around as we have model builders around because we all have our own personal biases and experiences, and they form the information processing that leads to the implicit model. Formalizing that makes the procedure explicit. Coming from the implicit to an explicit model means that we have to find a way to communicate our mental model with others. In order to communicate it, we need a language for precise description of such a model. And the language we use, which may be verbal, just using sentences, describing cause and effect relationships, or may use other symbols, graphical symbols, or may use mathematical formulas and symbols. This language must be understood by the model builder and the model user. But the process is always such that we have a personal view from the real world system, and this personal view forms the implicit mental model at the back of our mind, and that's the basis for the explicit model, and that's the reason why models are normally quite different and are always biased by the personal experience of the model builder. And what we can always conclude, also conclude from that, that there isn't a wrong model or a right model. It captures different aspects. There's different aspects that are incorporated in the model, and others are meant to be less important and are therefore left outside the model. But there's never such a thing like a completely correct, a completely right, or a completely wrong model. When we develop a model, we don't do that just for fun, but normally we do it because we want to use these models in problem solving. And there's another aspect we have to keep in mind. How do we use models in problem solving? This shall represent the real world system. Now through our process of model building, we form a quantitative formal model. And while we are doing this, we detract all aspects which we think are not necessary, which we may call abstraction. So we have a simplified image of the real world system which forms our quantitative model. Then we apply this model along with some mathematical algorithms to calibrate it, or algorithms which we use to come up with optimal controls, in order to derive results from the model. Since the results are derived from a formal model, we call them formal results. And then we will use these results for our problem-solving procedure, but that means we have to retranslate these results into the context of the real-world problem at hand. And the more abstraction we have used in the part of model building, the more necessary it will be to interpret the results and draw conclusions for the real-world system, instead of actually trying to directly implement formal model results in the real world. So if you look at this feedback loop, you might conclude that it would be always wise to keep the degree of abstraction as low as possible. Develop an isomorphic model which captures all aspects of the real world system, because the closer the formal model is to the real world system, the less interpretation is needed to convert the formal results into conclusions for the problem that has to be solved. However, there is a trap, because the way we solve problems is via simplification. The only reason to develop a model as a simplified image of the real world is because we understand the model better than the real world. And of course, running model experiments is less costly than running experiments in the real world system in most cases. But it is the simplification that gives us an idea of what the relevant cause and effect relationships are. The more complex a model gets, the less we are able to understand it. If it gets as complex as the real world itself, it wouldn't help us to wouldn't help us to solve the problem. And therefore, finding the right degree of complexity, the right degree of simplification, always is an issue. It's an important issue. And my personal experience in this context is, well, keep it simple. Even simpler. Because the more complex the model gets, the less it often helps to understand the world.
Yes, but then how can we understand the logic and that we need to make simplifications, obviously, to make the global, to make the model understandable? But how can we jump from formal results to conclusions that the real world is simple? Because the degree of complexity then gets really high, and then how can we reinterpret very simple results for the complexity of the world and know that we are drawing the right conclusion?
Let me try to give you an example. You could develop a model that optimizes, that gives you a mathematical optimization of a cropping system, of a crop plan, crop mix. So and so many hectares or acres of this crop and this crop and the other crop. If we do that, we normally distinguish between wheat and barley and other crops, and then we end up with a production plan that gives us the share of the total acreage to be allocated to each of the crops. Translating that into the real world means we go to the farmer and tell him what rotation to use. But the optimal result may be use 6.78% of your total acreage for planting barley, for growing barley. How you do that, how you interpret that in terms of a rotation. That's the interpretation you have to do. Because you have to go out to the farmer and tell him, well, derived from the logic of the model, which also tells you the sequence of competitiveness, the sequence in which the different crops have entered the optimal solution and so on. From this, you could derive a strategy to use to allocate crops to your fields. The other way would be to increase the complexity of the model, by not saying you have 100 hectares of arable land, but instead we have 17 different fields, different size, different quality of soil, and so on. So you enter each field in the model. By this you increase the complexity of the model heavily. Would it help you? Probably not.
But the model really depends on the question that we are asking.
Right.
The aim of our research.
Right. Yes, but the problem of deciding how complex the model should be. And what you want to get out of the model, what you want to understand, still remains. Very often, we intend to build a model that almost perfectly tracks a historical development or the results from experiments which we have run. However, this may not even be the main problem. Why would you want to build a crop growth model that perfectly predicts the yield in the case that the weather pattern of the growing season is perfectly known? When you have to come up with your decisions on fertilizer application, on sowing dates and so on, you don't know the exact weather pattern in the future anyway. So even if the model would perfectly track a historical development, it would basically not help you solve your problem. If the model would be less complex, but match the correct issues, it would be of more help. In economics, we always have to do some sort of decision making in case of marketing and inventory management. Of course, people say if I would perfectly know the seasonal pattern of prices ahead of me, I could come up with the optimal date of marketing my produce. However, there is no perfect predictor. If I use an estimation procedure that, as we normally do, comes up with a model that would minimize the squared error, it would probably be less helpful for me to come up with the right decision than a model that only predicts the turning points right. Because it's the turning point that is it's not necessarily the distance from an observed time series that triggers the decision. In this case, it would be the turning point. As long as prices go up, I would keep the inventory. But I have to know when prices go down, then I would resolve the inventory. And therefore, I would look for a model that's good in predicting the turning point. And I would not give any attention to minimizing squared error, because the opportunity cost of being wrong are not a quadratic function of the deviation between observed values and simulated values. And that's why I say, well, we always have to look. What's the problem at hand? What is the objective for which the model is built? And only that can give us an answer on how complex what are the things we should keep in mind, and what could easily be neglected. Let's look at a little bit on what complexity means and how complexity is caused. It's non-linearity, and it's the dynamics of the system. And dynamics often occur as time lags, which actually cause complex behavior. If we look into dynamic systems, and I'm only talking about dynamic systems, dynamic representation of dynamic systems, because the systems in which we are involved are normally systems that evolve as processes and are therefore dynamic. Such complex behavior includes multiple steady states, or equilibrium states, limit cycles, chaotic motion, and all these things. And that can happen even with very simple looking models. How can models that capture the essential dynamics and nonlinear relations, if they are help us in thinking, support our thinking and problem solving? Well, the reason is that we are basically trained to solve our problems using monocausal relationship, one cause or one stimulus or one clause, and we are trained in linear thinking. I'm an economist by training. I was trained in linear thinking, which can easily be seen if you look at a simple model which is well known to each economist. This is just the demand function, and this is a supply function. Demand function representing the marginal benefit of goods which one can buy, and the supply function representing the marginal cost of production. While these two functions are linear, they need not be linear. However, the way we use this model, even if we would have non-linear function, would imply linear thinking. Why? Well, basically what we do with such a model, we look at the intersection and say, well, the intersection, that's the point where supply equals demand. And on the vertical axis, we have the equilibrium price. And on the horizontal axis, we have the equilibrium volume. So if firms offer their produce at this price, then the total volume they produce can be marketed. There will be nothing left in the inventory, and the demand will be completely satisfied. What we do using such a model is we only look at this equilibrium point. Look at it. Knowing, however, that this is the final point of an iterative process of trial and error, adjusting prices and adjusting volumes and doing the marketing. You try to sell your produce, come up with an expectation of the price you get, and then your customer says, no, I don't want to pay that, and then you start negotiating, come up with a price, and after a number of cycles of iterations, you may end up at this equilibrium point. Knowing that this is a dynamic process, which could be done in a short time only at an auction, but auctions are fairly rare events for marketing produce, we still only think, consider, only pay attention to this equilibrium. And then we use comparative statics, as we call it, to, for example, check what happens if, due to technological advances, the marginal cost of production are lower. If we have technological advances that bring up higher yields, then we would have a lower marginal cost of production, which would mean at the same cost we could produce more. And that, of course, would bring us to a different equilibrium point, which is now here at this intersection. So we would conclude that if a technological advance or a subsidy, factor subsidy for the farmers, would move the original supply function to this new location, then we would conclude that the new equilibrium price would be lower, it would be P2 star, and this would be the new volume. And since it's a higher volume, we would conclude that lower price and higher volume results in a higher consumer welfare. And since we don't pay any attention to the process, how the system moves from here to there, this implies the general assumption that independent from the starting point, this final point, this new equilibrium, can actually be achieved. However, this is an implication which only holds for linear systems. And only in the case of linear systems, we have just one stable equilibrium. There can't be more than one stable equilibrium in a linear system. And only in linear systems, the condition holds that this equilibrium point, the steady state solution can be achieved from an arbitrary starting point. If we have nonlinear systems, things are quite different. Then we may have more than one equilibrium, which can be stable, and it may depend on the initial conditions. Which of these equilibrium points is the one that becomes attractive in a certain situation? And that causes quite a different behavior. Let's illustrate that using models that come from ecology and from economy. Let's start with a very simple model of population dynamics. If we develop dynamic models quantitatively, at least the type of models we are talking about, the type of models that were used in the report that never grown, we have to represent them either in differential equations or in difference equations. This is the simplest form of a differential equation you can imagine. It's a linear differential equation that represents exponential growth. We solve this equation formally, we will come up with a formulation that gives us the population density at time t as a function of the initial value of the population at time 0 and the growth parameter, which is g in this case. And since we solved the differential equation in a way that we can represent the population density at any point in time as a function of the initial value and the parameter, this is called the initial value solution of the initial value problem. There are other solutions to differential equations, but that's the one that is of interest to us. In reality, we hardly find exponential growth. Normally, growth is limited. It's pretty easy to come from exponential growth to a limited growth, moving towards the logistic growth function originally developed by Perl. And the only thing we have to do is we have to make this reproduction factor a function of the population density. Just assuming in this case that the net reproduction rate falls linearly with an increase of density. That could be done by using this formulation. So G is R, where R is the maximum reproduction rate, times this term in brackets. And what you can see is that if the population density is close to 0, then we would multiply R by 1, and this term would be very small, so we are close to the maximum reproduction rate, which is called the intrinsic reproduction rate. And on the other hand, as soon as the population density approaches this parameter k, this term approaches 1, then we have 1 minus 1, and the term inside the brackets becomes 0, and therefore the net reproduction becomes 0. So if you introduce this term into our original equation, we have this logistic growth differential equation, which is nonlinear in its parameters, because if you multiply through, you have this population density in the raised to the second power. It's n square, which we have. So we have a non-linear function. What does that mean? It means, in the first place, that we now have limited growth. And as we already indicated, growth will be limited by this parameter k, because if n equals k, then the reproduction factor goes to 0. This bracket goes to 0, and whenever one of the products of this, one of the factors that make up this product becomes 0, we will have 0 at the marginal rate of change of the population density, and that's the case either when k is equal to n, that's the upper limit, or when the population density equals 0, that's at this point. So this is also an equilibrium point. And that's what I said. Nonlinearity always causes multiple steady state solutions. However, not all of them are stable. And in this case, the point down here is an unstable equilibrium, because if we enter one element, if nt is, at point 0 is a little bit larger than 0, then this process would start and would finally converge to the upper end, to the carrying capacity. This term K is called carrying capacity. In this form, the model is not really able to capture many things. However, logistic growth is a basic archetype which can be used in many instances to model development processes that are limited by some sort of carrying capacity. Mostly we have to add some extensions. And one extension which we might add if it comes to population modeling, we might add a maturation cycle by dividing, by distinguishing between juveniles and adult entities, and only the adult entities can reproduce. The easiest way to enter that in our model is via a time lag. So this now indicates the population density at time t minus the time lag of capital T. What does that mean? That would mean this term would be dependent on the population density capital T time units earlier. Okay. So that capital T could stand for a maturation time lag, the time needed to get from the juvenile state to a mature state. This simple addition to the model makes the behavior quite different, depending on how large this time lag is. If the time lag is very small, we still have the same behavior as we had already seen from the logistic growth model. However, if the time lag increases, all of a sudden, the behavior of the model becomes different. We now have cyclical behavior, damped cycles. And if the time lag increases even more, finally we end up with a limit cycle. We have cyclic behavior, and all the cycles have the same amplitude. That's what we call a limit cycle, which is already known as one of the so-called strange attractors. Not much with what we have added. And we have moved from monotonic growth to a limit cycle just by introducing a time lag. And time lags are present all over the place. If we start a production process, there is a time that elapses from taking the decision to start a production process until the time when the animal is finished and can be marketed. If we sow, there is a time lag that elapses before we have the harvest and so on. So time lags are present all over the place, and they are one of the causes that enter, that bring complexity to the models. Let's look at some more population models. Lotka and Volterra in the 1920s have developed a set of models that dealt with population interactions. One of the possible interactions is the interaction between a prey and a predator. Okay. Basically, the assumption is that in the absence of a predator, the prey population could grow exponentially. Assume that there was no predator, that is, y would be 0, then we only had this term different from 0, and we would have exponential growth. On the part of the predator, on the other hand, if there was no prey, we had exponential decay, which means that our assumption is that the prey could grow exponentially without any limit if there was no predator. And on the other hand, the predator is a nutritional specialist which needs the prey for feeding, otherwise it would be condemned to die out. Well, this assumption that we have unlimited growth with no predator is not one that's realistic in the world, but it's quite easy to change that by just entering a term that makes the growth of the predator population a logistic one in the absence of the predator population. Okay, if you take this model and look how it behaves, how the time response is for the prey population and the predator population, we see that when we started at any point, and the combination of the predator population and prey population, we have damped cycles, and they move towards an equilibrium, which is a steady state solution in this case. We could represent that in a so-called state space diagram, where we delineate the predator and the prey on the different axes, and all the points here mark starting points. Then we have the trajectories. So if we start here, we have along the time axis we have an increase of x, and then later on we have an increase of y also. And since the predator feeds on the prey population will be reduced, and then we have such a spiraling, and it all moves towards this center point, which is then the equilibrium. That's the steady state solution which we had in the time diagram. If we find such a time response, we're talking about a fixed point attractor. We have a nonlinear system, but it has quite a simple behavior because independent from the starting point, the system always spirals inward and ends at the fixed point attractor. Let's go to a model that is equally simple. However, it doesn't capture predator-prey interactions, but instead it models two populations, X and Y, that feed on a common resource. Okay. And the red marked terms here indicate the competition of population Y on X that comes from eating from the common resource. So, and alpha obviously is a competition factor. Alpha would be 0, then this term would not be of any influence, and then we would be back to logistic function. So without the competition between the species for the common resource, each of the populations would develop independently in this S-shaped growth process of the logistic growth equation. However, if A and B are larger than 0, we can have quite different situations, depending on the parameters. For some values of these parameters, where the parameters that are relevant are the specific carrying capacities for each of the populations, which is a function of body weight, for example. They have big animals that eat much and others, and therefore the maximum population density in a limited habitat is less, and others may be smaller, eat less, and therefore the number of entities may be larger. So it's the specific carrying capacities that matter, and it's the it's of course the competition factors that matter. Depending on these parameters, we may have quite different solutions. Nice picture, let's interpret them. This obviously indicates a solution where we have stable coexistence. no matter where we start, with what combination of population y and x we start, all trajectories end at the same point. That is stable coexistence. In other situations, we might find a different behavior. This is the situation where all trajectories end at that point. And this point says we have the population y at its carrying, at its specific carrying capacity, while x has died out. So here we have no competition, and we could of course construct a situation where all trajectories end at a situation where only the species X survives and Y dies out. And this is the most interesting case. What I told you is that it might well be that there are multiple steady states, and the steady state that is finally approached depends on the initial situation. That's the case with this parameter setting. If you look at the starting points that lie in the upper left half of the picture, the situation is such that the steady state solution would be up here, so only species Y would survive and X would die out. If the starting point is in the lower half, lower right half of the state space, then only population X would survive and Y would die out. It's all the same model, it's a small change of parameters. And the parameters that change, or whose changes may cause switching from one case to the other case, are, for example, the specific carrying capacities. Now assume that this is a natural system. However, we as human beings interact with this system, for example, by harvesting the common resource, by grazing, for example. And that would mean, if we do so, we would be an additional competitor that would eventually reduce the specific carrying capacity for one or the other population. If that happens, we could just accidentally change the behavior of the system in a way that the former coexistence, which might be the initial case, ends in a situation where on one field population X and on the other field population Y dies out, which we then realize and don't know what the reason for that was. And the reason why in one case only Y survives and in the other case only X survives may be because for some random reason we were either in this plane with the starting point or in this half of the state, the starting point. So if you're looking at models, at systems of that nature, interactions in ecosystems, you might be much more interested in figuring out what's the frontier where the system switches to another case. So what are the relevant parameters? Then trying to most accurately trace a historic situation. Shouldn't help us much. We have to get the dynamics right in order to be able to detect where the critical borders are, which we have to consider. Okay. Let's go back to economic systems. This again captures the supply and demand system, but now in a dynamic fashion. This may be the demand function. This is the supply function. Now I've named them, denominate them a little bit different. This is still the demand function. But here I say, this is the function that describes marginal costs, by which the producers decide how much to produce.
Sorry, just a question to the slides before. I'm just thinking that this represents just the volatility of the mathematical models, but not so much the volatility of the what could happen in reality.
At this point, it is a formal model, so it's not the volatility, it describes the sensitivity that the model has for if you change certain parameters.
Right. So, I mean, I could imagine easily much more complex mathematical models, where at the end I would say I couldn't say anything about what's going on in nature.
Yeah.
So it means there must always be, I think, let's say, it must be compatible somewhat.
Right. In nature, you have many interacting populations. You could always say I have to add another population to my model in order to capture what happens. But also in ecosystems, we have relatively autonomous systems. The degree of interaction, of competition between populations is different. And we have to figure out what are the important aspects. And then at least we can obtain orders of magnitude for these turning points.
Okay, what I just want to point out is that there should be an adequacy of the modeling and the reality aspects, and that is I think that is the prominent point here, because otherwise, I mean, I'm just how to say, I make myself afraid of mathematical implications which will never arise in nature.
Yeah, but my argument would be, instead of trying to make the model more complex, in that you say, well, I have to explain how this competition comes together, it's more important to get the dynamics right. Now, if you run 2,000 regression analyses with entering many variables in order to explain this competitive term, it may not help you a lot. It's much more important to get the dynamics right. And then try to get an idea, because what you can always conclude is that if you come close to this borderline, the system gets more vulnerable. So stay away from the vulnerable point, but you have to identify it. You have to say what are the main variables which you can observe that tell you whether you move towards this vulnerable point or whether you are ways away from it.
No, I mean complexity also comes from learning.
Yes.
And all these models, may they be linear or non-linear, they don't incorporate this learning. They don't incorporate this stopping at a point, and changing the direction at a point, and so on and so on. So, insofar they are just extrapolations from mathematical, how to say,
yeah. Fortunately, populations in ecosystems normally don't learn a lot. They just survive or die out. It's different if you move to modeling human societies, then this becomes a very critical factor. Then you always have to consider that learning is a factor, and that the modeler itself is part of the system. And by developing the model, we give an instrument for learning, and if people actually do something with the model, then that will change the system. That sort of changes does not occur in technical systems and not in ecosystems, because we have survival of the fittest as a basic rule, and then we have mutations of populations.
Whatever this means. Fittest. I mean.
Yeah. Yes, that is a complexity in itself, but we don't have this learning aspect which we have in if it comes to modeling human societies. Mm-hmm. Then we have to consider this aspect. In a moment, I'll try to capture a sort of learning in trying to model decisions made by a decision maker. This is a simple demand and supply system. And all that it differentiates from the static system we had at the wall before is that we now take the process of adjustment of price and quantity, so to capture the dynamics of price adjustment. And we also capture the fact that between a decision to increase production because the observed price is higher than the price it was in the past, between this decision to adjust the production to the changed price, we have a delay which captures the production time, the necessary production time, before the produce actually appears at the market and has an effect on the price adjustment process. Okay. And what the assumption is that once the decision is made, for example, to buy piglets, then the finished pork, the finished hogs will appear on the market. As soon as they are in the pipeline, it will take some time, and then they will appear on the market. And what we see later is that we say, well, there are other influences from other markets, if we look at one commodity only, which we model by sort of random shocks. Let's look at the model in the first place. If we start it away, apart from the equilibrium point, the model exhibits damped cyclical behavior, damped cycles, and finally approaches an equilibrium point, which is actually the intersection of supply and demand function. If we could also represent that as a state space diagram, then we also would have this spiral to a fixed point attractor. Now, if we assume that there are other commodities, this may be pork, then we have substitutes like beef, and which means if the beef price is low, then people eat more beef, and that will reduce the demand for pork and the other way around. And in our single model, that may cause a deviation from the equilibrium. Even if it's close to the equilibrium, such cross-price elasticities will lead to deviations from the equilibrium. This is the same model. The only difference is that I have added some shocks after certain periods of time. And what we see is irregularities, specifically showing up in the price, and permanent cyclical behavior. If you take this picture and interface it with a time series of hog prices for finished hogs in Germany and other prices of Europe, they look pretty similar. And that's what we have concluded years ago. So all this type of behavior, adjustment, and the external shocks that come from the interfaces with other markets, with substitute markets, we have these permanent cycles, which are well known as hog cycles. Now, if the hog cycle is really generated that way, so it's caused mainly by external shocks, we could come up with policy measures to stabilize it, like buffer stock policies. Say, well, price is above what we have estimated as equilibrium price. We could release inventories, and if the price is below, state could buy some pork and put it in an inventory in a warehouse in order to stabilize the price. Such policies, however, only work if these cycles are really caused by external shocks and are not immanent to the system. In our case, they are caused by external shocks because the model was inherently linear. It was simply a linear model. However, this model did not take into account the way farmers formulate their price expectations, and it did not take into account that we have short-term decisions where we adjust the production level within the boundaries of given capacities, and long-term decisions caused by investment. Now the only thing we have done here is we have expanded this model by introducing investment decisions and long-term price expectations, where long-term price expectations are modeled by exponential smoothing in an adaptive procedure. So the farmer learns from observing the past and extrapolates in the future. And then these long-term price expectations determine investment decisions in a way that the higher the expected profit is, the more investment will be undertaken. And this builds up production capacities. And then we assume that once the production capacities are there, they will be utilized as long as the variable costs are covered by the price. And if we assume a highly specialized industry with high fixed cost and relatively low variable cost, that means even if they make losses on the balance sheet, they will still continue producing as long as the production capacities aren't worn out, as long as they are within their service life. And therefore, we may have inherent cycles in the system. Okay, otherwise, production decisions are then taken by assuming that if long-term prices go up and short-term prices are below the long-term expected prices, short-term prices will go up also, and the other way around. And that is used to adjust the production within the existing capacity limits. Then, of course, we consider the time lag that is necessary to actually carry out the production. And then we have the process of price determination, which is the same process that we had before, and we have a demand function. So what we have added is a feature of dynamic models that often happens, in that we have a combination of fast and small moving variables. The fast process is the short-term adjustment of production within the limits, in the given limits of production capacity, and the long-term, 15 years or more, is the investment decision. Because the investment decision is taking, I think the average service life was assumed with 15 periods or so, and you have the capacities on board, and as long as they are there, there will be production even if the prices are fairly low. So what's the difference in the situation? Depending on the set of parameters, we will have all sorts of behavior, where the cyclical behavior which we have here is inherent cycles. It is not caused, there's no external shock considered. It just started at a single point, and we have this cyclical behavior in price, in desired production, that's before the time lag, and in the built-up capacity investments. And this is the situation where we have used only long-term price expectations as influence on the production decision. So we have assumed that people project prices in the future, then from this derive their investments, and then do not react with short-term production adjustments to short-term price movements. It has always been an argument that that the hawk cycle should disappear as soon as we only had large specialized farms which would not react in the short term, but still would continue producing, no matter whether the short-term prices are low or high, above or below the long-term expectations. The model result indicates that's the other way around. If nobody adjusts the production in the short term, then we have these limit cycles. These are indeed limit cycles, which is already a strange attractor. If we vary the expectation parameters, use long-term and short-term expectations, we have sort of superimposed cycles, short cycles and long cycles, but it's inherent cycles. The system doesn't move towards an equilibrium point. The most interesting part is this one, where we have created a situation with scarce financial resources. We have done that by limiting the maximum investment per period, which is a situation in which we could move if we have high interest rates that limit the investment that can be undertaken by farms or other situations. It's the opposite like as we have right now in Germany. If you have this situation with scarce financial resources, we have chaotic motion. This is deterministic chaos. At least the statistics that we have taken from the results of the model indicate that this is chaotic behavior. This is all done still with a relatively simple model and using parameters which are not out of the ballpark. We have assumed that we have a highly specialized industry, high share of so-called sunk cost. So we have relatively low variable cost because it's highly automated, but we have high fixed cost because we have high initial investments, and there is no easy way to use a hog barn for any other production. The only thing that you could do with it is just tear it down. There is no other use as a warehouse or whatsoever because the roof is so low. Okay, what does it tell us? It tells us that we have to really be careful in inspecting what really drives the dynamic of the model, because if we have inherent cycles, our buffer stock policies would not improve the situation. They would even worsen it, because we would always be, or in many cases, we would be anti-cyclical in our decisions on the buffer stocks and developing the buffer stocks. Instead of being, we would be cyclical, pro-cyclical, instead of being anti-cyclical, and would therefore even amplify the cycles, the amplitude of the cycles. The only situation where the system moves towards an equilibrium after an initial shock is where we have very long adjustment time for price expectations, which is actually a situation where we assume that people do not react at all to price movement, only in very long time decisions. Then we are basically back to our originally linear model. This is not linear, but it is almost linear. It's linear at least around a working area, in a certain working area. Then we have this situation. Okay, so what can we conclude from these models? It doesn't, in many instances, it's not so important to be able to actually accurately trace a historical development or reproduce experimental results. More important to get the dynamics of the model right and ask for the right questions. I've done just lately empirical analysis in taking price theories for hog prices in Germany for the last 25 years or so, and trying to figure out the type, the nature of the attractor, which is a specific task using nonlinear time series analysis. But the basic idea behind that was that I wanted to figure out how many variables do I need to model the industry so it gives me a time response that has the same properties than the time response I could observe. Not the same time response, Because if the time response is chaotic, and the time series looks like it was chaotic, it is not predictable anyway. However, even a chaotic time series moves in a certain range. And there are certain sequences that can be followed. And then the idea is to identify, in this case, the properties of the attractor, to put it in technical terms. And if I know the dimensionality of the attractor, in this case it indicated to me, well, it's basically 3 cycles. So it's basically 3 cycles modeled by at least 3 variables, endogenous variables. And these are enough. This number of variables is enough to capture the dynamics of the model. To go back to our model, what I have created so far is pretty similar to this model of the industry. We have a long cycle, which is the investment cycle, a medium one, which captures the adjustment of production, which is roughly 6 months, half a year or so in bulk production. And we have a fast variable, which is the price adjustment on the market. Because in a situation like in Germany, all producers, all actors on the market can go to the internet on Tuesday, and they have the actual prices that have been notified from the last week. So we have a price reaction, a price adjustment within a period of a couple of weeks or so. That is the fastest reaction. So if you capture, and that told me I have to capture the price adjustment, the quantity adjustment, and the investment. Basically the 3 functions, and some additional, some auxiliary variables. And that would be, and with that I should be able to create a dynamic behavior that has the same properties than the time series. And so far, the statistics of my model results are similar to the statistics of the real world behavior. So it seems to be quite successful, not at the end, but at least towards the end.
And the problem that you just mentioned is again validation.
Yes.
And validation of a model, which you just mentioned, is validation of historical.
No. In this case, it's not validation. Validation, I could have analyzed it.
I wouldn't say that is so, but what you just mentioned, how you validate your model is by looking how good you...
Yes, but I'm not looking to the goodness of fit. I'm looking to a model that captures the essential properties. And the essential properties, in this case, is give me the dimensionality of the attractor in the first place. I want to know what the nature of the attractor is. Is it a chaotic one? Then it's a chaotic one. Is it a limit cycle? Then it's a limit cycle. So, and I want to know what the dimensionality of it is. And that is not the same than maximizes goodness of fit. And the second step in modeling has the following aim. I want to derive a model for the industry which indicates me what are the 2 causes of this cycle. And
What had been?
yes, but since we still have that, even after BSE crisis and so on, it still is there. The main cause seems to persist. And I tell you what my hypothesis at the moment is. That is in part technology driven, because we have this highly specialized technology that creates 80% sunk cost. A second cause is a behavioral one, which is a quite natural one, in that after a period of high investment, we have a period of financial consolidation. Because normally high investments go along with increasing the amount of loans, and then you need some time for payback for financial consolidation before the next investment cycle starts. And since farmers act liquidity oriented rather than oriented towards profitability, we have these investment cycles. And the most important point, the most sensitive parameter, is the elasticity, price elasticity of demand. Demand is price inelastic. German consumers eat pork no matter whether it's cheap or expensive. If they would react more price sensitive, the cycle would disappear. So then we can start thinking about what we should do. Should we teach the consumers, change the technology? At the moment, my best guess would be change the technology. Let's change the technology. Let's use different constructions of hog barns, so we could have we could switch utilizing it in order to lower, that would lower the degree of sunk cost. And of course we could try to change financial regulations in order to influence the investment decisions. But at the moment I would try to I would encourage the ag engineers to develop new types of hog barns, new types of pig barns. So in case of like with a higher roof, so in case the pig business doesn't generate profits anymore, just convert it into a warehouse, put it next to the autobahn, and then convert it into a warehouse and rent it out as a warehouse to some logistic company or something like that. Which you can do with cow barns, for example. They are big enough.
But before you recommend what you would change, you have to know what the problem was, and I didn't get it.
But the problem is that everybody thinks that large price movements that show up reduce the welfare of actors. Okay, if you have large price movement, that creates uncertainty on the part of the actors, on the part of producers. If uncertainty increases, then the producers want a risk premium, and this risk premium must be implemented in the average price. So the average price is higher, and the consumer welfare is lower. So if you reduce the degree of uncertainty, that's the general idea behind. If you reduce the degree of uncertainty, then you can increase consumer wealth. That's the idea.
Small question. I think I will drag a little bit the conversation at the beginning. You said that modeling complex systems has two parts. One is the conceptualization and then the instrumentalization. So far we have an insight on the instrumentalization.
Yeah.
Now, and you even said that you can reduce the complexity until extract 3 key variables who could depict the functioning of the whole system.
Right.
Yeah, then the big question comes, okay, that's conceptualization. We have to choose the 3 ones.
Yeah.
How to do that? How to know which are the 3 ones? How to conceptualize the model in order that captures its complexity and we do not leave out what is key.
Yeah. But the first thing is clearly define the problem at hand. Not just say I want to develop a crop growth model for the sake of having a crop growth model. Ask yourself what do you want to do with it? Do you want to use it on a global scale to forecast global agricultural production or the volatility of agricultural production? That depends, of course, on weather patterns, which is certainly a relevant task these days. But that's different from developing a model that should be used by a farmer or an extension agent to derive a pest management strategy, a pest management program, or a cropping plan. So in the first place, ask yourself, what's the model developed for? What's the task for developing the model?
Yeah, but Professor, that whoever the actors are will give different answers. That's my kickoff for the second question. Then it's not participation a way to capture all these different perspectives and afterwards prioritize them and then go to the simplification, to the modeling itself. Participation would be an option?
Yes, if you get the participation is something that has the ability to give you the right answers to the question, what are the main driving variables, but it often has an opposite effect, because people tell you what else is important, and this is important, and this aspect is important. So you end up with many more aspects in your model than you originally thought, and that doesn't help you solving the problem in many instances. So I like the dialogue, I like participation in the early stages, but then I want to have a long period where I just think, and I go out, ask questions if I don't know how to go from where I am, but always being involved in the participative dialogue may sometimes confuse the situation. And what the other thing that I think is important, if you want to end up with a quantitative model, you have to learn, you have to develop a knowledge of the syntax. So you have to. I came with decades of experience. I can take my model archetypes from the shelf. I know there is a set of differential equations, and if I use that with a certain parameter setting, that's the behavior that this box, that this black box in some part of the model creates. And it is important to have that knowledge. But it's like a musician. If you are a musician, you look at the partitur and you know, you hear the concert, you hear the music. If you are not a musician, you are not trained in this field, you can still try to check what the tones are. You will never be able to just look at the sheet of paper and hear the concert in your ears. So, and therefore, there needs to be a training effect. So you have to work with these instruments. You have to learn the instruments in order to come up with a. If you know, I need something that shows a certain behavior. It's good to have a mathematical formulation in the back of your mind that does it.
Could you shortly explain again what strange attractor is?
Strange attractors are attractors where the system still is stable. Okay, an unstable system, if you look at the state diagram, would spiral outward, which means that one or more than one of the state variables would eventually approach plus or minus infinity. Then it would be unstable. The system is stable as long as all state variables stay in certain boundaries. But if the trajectory is an orbit or is some sort of a torus, without, in the case of a torus, without possibility to actually predict with accuracy in the real world system. You can always predict what the model does because it's deterministic. But such systems are sensitive to starting values. in systems that don't have these strange attractors, such systems are conservative in the way that errors in setting the initial conditions become smaller in the course of time. So large errors in the beginning are reduced to small errors, small deviations in the course of time. Systems with strange attractors are systems that are dissipative in the sense that small initial errors become large errors in the course of time. And the first type of attractor that is called a strange one is this limit cycle attractor, where a limit cycle is defined as a closed orbit. If you have just two state variables, if you have only two state variables, then you can depict it in a two-dimensional diagram. If you have more than two, you either use projections of two pairwise, or you have to come up with some mathematical definitions of what the nature of the attractor is. A limit cycle is an attractor where whatever point you choose as a starting point, you're always ending up in a closed orbit and in the same orbit. So if it's a cycle or an elliptic trajectory in a two-dimensional state space, this elliptic figure would not be dependent on the starting point. So that's a limit cycle. And what comes beyond the limit cycle is deterministic chaos. And in deterministic chaos, you have movements in a certain boundary, and you have repeating patterns. But you never know which pattern comes first and when comes the next one. If you look at it, there is a repeating pattern, but you cannot exactly predict it. You cannot predict the turning points. In the model, of course, because the model is always deterministic, you are simulating on a digital computer. But in reality, you couldn't, because of the limited accuracy of determining the initial state. If you could exactly determine the initial state, even if you have turbulent fluctuations like in the atmosphere, if it comes to weather prediction, even if you had a perfect model, you would not be able to predict, because we have limited accuracy of measuring the air pressure or whatever at a certain spot. And a small error in measuring the air pressure or wind speed at a certain spot would cause a large deviation in the course of time. That's why weather predictions only work for short periods. The longer the period is, the larger the error becomes.
Yeah, thank you for your presentation. I would like to know, can you hear us again with the abstraction phase? Is that based on your economic background, or based on participative approach, or?
At least the basis must be the knowledge about the context in which your model works. It's either it's your personal background, like my background in agricultural economics, that tells me something about how the hog industry works. So I have experience in how the hog industry or the pig industry in Europe is set up and how it functions. Or you have to acquire this knowledge by asking experts.
But how to define the principal variables models? Is it based on econometrics? I don't know.
No, the first thing, if you go about modeling, the first thing you ask yourself is what are the basic variables which I want to trace by the model. And then you define the nature of these variables. See, one way of doing that is using diagrams like this. Well, this is a simple population model, and so what we first have to do is we define what are the variables of interest. In this case, population density, the birth rate, the death rate, and food supply. And you have to ask yourself what are the relevant variables first. And then, of course, modeling always involves defining causal relationships between those variables. And the first way of illustrating such causal relationships is using arrows and plus and minus signs, which means that a high birth rate causes the population to increase. A high death rate causes the population to decrease. That's the negative side. And we have a cause and effect relationship in the way that the death rate causes a change in the population. However, we also have the opposite relationship, because if we have constant, proportional birth rate, always 10% in each period, and that means a high population density implies high absolute number of deaths. So we have the opposite relationship also with a plus sign. We do that, and whenever you have this cyclical figure, you know that is a feedback loop. And wherever you have a feedback loop, then you know from a modeling point of view that the variable which stands in the center of such a feedback loop is a state variable. And so that would be the first thing to develop such diagrams. And well, if you look at such diagrams, you could even come up with some conclusions, if they are simple enough, how they behave. These are nested diagrams. We have a number of feedback loops. If you multiply the pluses and minus signs, you end up with a conclusion whether it's a positive feedback loop or a negative feedback loop. This one is a positive population, birth rate population, which means if you would only look at that, that would cause exponential growth. So it would be an amplifier loop. And this minus times plus or plus times minus ends with a minus, so that would be a stabilizing loop. And then you have another feedback loop where you say, well, if I have a constant total supply of food in the habitat, then the more entities I have in the population, the lower the food supply per entity is. So high population means starvation, no food supply per entity. And on the other hand, high food supply means high birth rate and low death rate. So again, you have stabilizing loop. This one stabilizing. This one is not stabilizing. This one is an amplifying, but minus, because minus times minus is plus. And altogether, you could conclude that probably this must be a stable system. And the next step would then be, well, I've identified my feedback loops, so I have to develop a scheme for developing the model. Going to tools which we have, in this case, like the system dynamic tools, we could then change the nature of the variables by identifying what are the state variables, what are stocks or levels. And they have something to do with feedback loops on the one hand, and on the other hand, it's a matter of how you measure them. Rates are more normally measured as numbers per unit of time, whereas level variables or state variables are normally measured by units. Population is entities, population density is entity, it's not per unit of time. And then we would say, well, this is a central state variable of the system. And then if you have identified the state variables which you want to model, you could move to a general form of modeling state variables. That brings us to the system dynamics modeling concept, in that we say, well, a state variable is always changed by inflow minus outflow. So each state variable can be represented as a differential equation, that we say the marginal rate of change per unit of time is input minus output. Or we could, by the same token, we could represent it as an integral equation, where we say the level at a certain point of time is the integral over input minus output. And then, of course, we have to add other functional relationships, because we have to define the input and the output as a function of other variables, of input causes and output causes, and then as of the model. So in our case, the input would be birth, the output would be death. And then we had to define the functional relationship, which say the input, the birth rate, is some function of food supply per entity, and the death rate is some other function of food supply. That would bring us to the next step of modeling. Using the tools which are around at the moment gives you the opportunity to actually use this form of graphical modeling. The tool I'm using in teaching, classroom teaching, and also for doing prototype modeling I use, is Vensim. But the reason why I use Vensim is because there is a public domain version on the market. It's not public domain. It's called a personal learning edition, PLE. And the personal learning edition is free for non-commercial users. So you can use it in the academic world. You can also use it for developing research results, but it's not for commercial use. We're using it in the academic environment. It's perfectly all right if you use it in a company, in a private company. It would not be all right. It would be a violation of the license. But this software system is not one that is it's not the one that is easiest to use, but it's the most powerful one that is available for free. So that's the reason I'm using it. Sometimes I hate the dialog boxes because they are overloaded. It takes always 5 minutes to figure out what the right box to check is. But it is a very powerful system. It's a nice system to develop now. Plus, there's a variety of models around which are very useful. I said that it is important. I think it's very important to train yourself, to work with such a system, to play with models. This is a system zoo. There's a book around, written by Hartmut Bossel and some other people. It's available in a German version and in an English version. And it comes with a big bunch of models. For example, employment, productivity, production.
The models are already in Vensim?
They are in Vensim, yes. Just here are eco models. For example, what we have? Soil water model, humus model. They are already in Vensim. They are in Vensim, ready to run. Mostly not the models which you really want, which exactly represent what you want to model. But they give you a lot of.
But one can get some sections of the model,
yeah,
and modify according to the process one needs.
Yeah. And yeah, they are ready to run. So just check run the model. model. Check model, let's check simulate. There we go. So now it's simulated and it should have some graphs. We have graphs.
How many were
Don't ask me what is in this graph at the moment.
Okay.
But it's and it, as I said, there are 3 books, relatively cheap, the area of 20 euros or so, not more than 20 euros per piece, which where these models are described, and you can take parts of them, and otherwise use them, and it is some very nice ideas contained in these books. Hartmut Bossel was a professor emeritus from University of Kassel, and he also was into quantitative modeling for 30, 40 years. That's written a number of books on that.
Thank you very much, Professor Berg. It was truly a great honor having Professor Berg here again with us. Well, before everybody goes, I would ask for a applause for Professor Berg for this. Thank you very much for coming. I wish we'll be a second time, third, fourth. Thank you.